Right, good afternoon and welcome everybody. Welcome to the very badly misquoted from Star Trek, "It's Java, Jim, but not as we know it," because the original quote that people like to say is "It's life, Jim, but not as we know it," and that's actually a misquote anyway. But anyway, the idea behind this presentation is to talk about Lambda expressions. And so what I've done in terms of the agenda is divide it up into three parts. First part, we're going to talk about the details of Lambda expressions. So who here is using JDK8? Okay, good. So we'll talk a bit about the details of Lambda expressions from the point of view of what they are and how you use them and so on. Then we'll talk some about the performance of Lambda expressions, because the way that they're implemented is not quite how you might expect it, and so there are some interesting details that we can discuss when it comes to how lambdas perform compared to the equivalent anonymous inner classes. And then the last part of the presentation is how far can we take lambdas? And this is where we get into the "it's Java, Jim, but not as we know it." And the way that I've kind of divided this up is that the first two parts are what I describe as interesting and useful. The last part is interesting but not so useful, because nobody is going to program in Java the way that I'm going to show you at the end of this presentation. If you do, you're doing it wrong. Right, so let's start then with Lambda expressions. Now, since you're using JDK8, you will be aware of some of this stuff, but it's worth talking about this in a little bit of detail. So what we had before JDK8 was the idea of anonymous inner classes. And what we could do there is we could create a reference to an instance of a class that implemented a particular interface. And in the case of this one, it's an anonymous inner class that has a single method that needs to be implemented. So rather than actually having to either create a new class which implemented that interface and then instantiate it, what we can do is we can simply say, create me a new runnable, which is the interface, and I want the method of that interface to be implemented this way by having run, and then we're going to do some stuff. And then we'll start the thread in the usual way. Problem with this is it's rather verbose, because we have to explicitly state that the interface we want to implement is runnable. We have to have brackets in there. We have to explicitly put that the method is called run. It's of type void return, and then we have some stuff that we want to do. So there's a lot of stuff in there which we don't really need. And that's what Lambda expressions are all about. It's a new style of doing that kind of thing, but in a much simpler form. So now we know that we can use a Lambda expression to do that. So we have a single line now where, rather than having all that extra stuff, the compiler infers from where we use that particular Lambda expression what the type is. So the compiler knows that thread takes a runnable as a parameter. So it knows that the type it's going to have to create is a runnable. And then we tell it what the implementation of that method is, but without explicitly saying what it returns, what the parameters are, and so on. So much, much cleaner, much, much easier to use. If we dig into a bit more detail about what that really means, what we're doing here is having a simplified way of representing behavior in Java. Rather than it being state, we can assign behavior to a variable, and we can pass behavior as a parameter to another method. So this has a lot of benefits in terms of what we want to do. And in terms of where we can use a Lambda expression, we can use a Lambda expression anywhere where the type that it's going to represent is a functional interface. Functional interface is one which has only one abstract method. Now, prior to JDK8, it was pretty easy to spot a functional interface because it only had one method defined in it. In JDK8, in addition to introducing Lambda expressions, there is the idea of static methods and default methods in interfaces. What that means is that you now have behavior included in an interface. And the kind of net effect of that is that you have multiple inheritance of behavior as well as multiple inheritance of types, because interfaces allow you to have multiple types associated with a variable. What we don't have in Java is multiple inheritance of state. So that's the important thing. It's not like C++ where you have true multiple inheritance. Java, you've got multiple inheritance of types, multiple inheritance of behavior, but not multiple inheritance of state. So in JDK 8, if you have a single abstract method, then you can use a lambda expression to represent that. And the key thing about that is that the body of the lambda expression is the implementation of that single abstract method. The other thing about this was that in terms of the design, this is actually a much simpler way of allowing people to have behavior assigned to variables and passed as parameter, rather than having to introduce a new functional type to the language, because that's another alternative way of doing it. Other languages do have a true functional type, but in Java, because it was an existing language, they didn't want to add a new functional type, so they've done it through the idea of lambdas. So in terms of the syntax of a lambda expression, it is like a method, but very importantly, it is not a method. So it's not associated with a class. That is a very significant point. We'll kind of come back to that in a moment. But a lambda expression is a functional interface type. It is not associated with a class. In terms of the syntax, what we have is the left-hand side of the lambda operator are the parameters that we're passing to our method-like object, and the right-hand side is the body of our method-like object, but not associated with a class. So in terms of its structure, it is very similar to a method. So it has a set of typed parameters, it has a body, has a return type, and it can throw exceptions. So all of those things are exactly the same as a method, but because it's not associated with a class, we don't call it a method. The other thing about this is that it is a closure over values, not a closure over types. What that means is that if you look at how you can use a lambda expression, you can reference variables from the surrounding scope. So you can reference variables from outside of the lambda expression and use those in your lambda expression. But there is a restriction on that. If you go back to anonymous inner classes, the way that you could access variables in the surrounding scope was only if they were marked explicitly as final. So their value could be set once and you couldn't change it. That way you couldn't change the value inside the anonymous inner class. With lambda expressions, the same thing applies, but the rules have been relaxed a little bit. So now the variable has to be effectively final, which means that it can be marked final, or if it's not marked final, it must behave as if it was. So its value can only be set once and it cannot be changed. Right, so let's talk a little bit about capturing lambdas. So a capturing lambda is one which uses a variable from the surrounding scope. And when I started using lambdas, I wrote a piece of code which is very similar to this. So I had a class which I called data processor. It had a current value int, and then I wanted to process something, so I used a lambda expression and I did current value plus plus. I compiled it, I ran it, it did exactly what I wanted it to do. I thought, yes, great, my code is good. Then I thought about it a little bit more. I thought to myself, hang on, that shouldn't work, because current value is not effectively final. Now I've just told you that we have closures over values, not closures over types. So how can that work? How can the compiler do what I don't expect it to do? And it turns out, I did a bit of digging on this. It took me a while to find out what was happening. It turns out that the compiler does something on your behalf. And I'm not actually convinced that this is a good idea, because what happens is it actually inserts a reference to this in front of your variable. Now, remember that a lambda expression is not associated with a class. So it's not like an anonymous inner class where there is an instance of that anonymous inner class, and if you use this, it would refer to the instance of that class. A lambda expression, if you use this, it refers to the class of the surrounding scope. In this case, it would be the data processor. So if we insert this in front of current value, this is an effectively final variable. So we can then use the effectively final variable, we can indirectly access through that into current value, and we can increment it. So yes, it solves the problem for us, but I don't think we want the problem solved, because the whole idea of lambda expressions is we're dealing with functional programming where you shouldn't be modifying state. This allows you to get away with modifying state when you shouldn't really be doing it. So, like I say, I think this is a bit of an iffy call, because it also introduces code which you're not seeing in the actual code that you write, so you're not aware of that reference being inserted. Method references. So this is the idea that where you have a Lambda expression, which is simply using a method on the parameter that you're passing to it, or some other forms of that, which we'll come to in a moment, you can simplify that by eliminating some of the extra code. So in this case, I've got a file filter X, and I want to represent that using a Lambda expression where I take file F, and I'm going to call the canRead method on F. I can simplify that by simply saying file, which is the type, colon, and then canRead. And that's equivalent to the Lambda expression above. In terms of the way that you can use method references, there are actually three distinct ways that you can use them in terms of forming them. And so the idea of this is that you have a target reference, double colon, and then the method name. So it's the method name that's going to be called on the target reference. As I said, there are three kinds of these. One relates to static methods. One is where you're calling an instance method on an arbitrary type, and one where you're calling an instance method on an existing object. And if we look at the rules for construction of those, most of it's fairly straightforward. So in the first case, if we're dealing with a static method, what you're going to have is a Lambda expression where you've got some arguments, and then you've got a class name, and then you call the static method on that with those arguments. So to convert it into a method reference, you simply use the class name, double colon, static method name. Great. Going to the bottom, where we're using an existing object reference, what we can do is the same thing. We can say, okay, we've got some arguments, we've got an expression which represents an existing object, we're calling the instance method on that with the arguments. So the way we construct the method reference is basically the same, except rather than using the type, we use the object reference. The one in the middle is slightly more complicated, because in this case we have a set of arguments where the first argument is the type that we're going to call the method on. And then we have potentially more arguments after that. And it's those rest of arguments which we pass as arguments to the instance method on the first argument type. Okay, now that all looks very complicated, so I'll show you some examples and then it makes it much clearer, or at least I hope it does. So the first, calling a static method, we've got string s as our parameter, and we're calling integer.parseInt on s. So very simple, we can convert that into a method reference by saying integer double colon parseInt. The second one is where things are a little bit more complicated. So we've got string s and we've got int I as parameters. And what we want to actually do in the body of the Lambda expression is say s dot substring of I. And we can convert that into a method reference by using string, because that's the type of the first argument, s, and call substring on that, which will pass I as the parameter to the call. And then in terms of the last one, if we've got an existing object, if we want, in this case, we've got an axis A, and then we're going to call getLength, which is in the class which we're actually running in, we can use this as a reference, because again, the Lambda expression is not associated with the class, so this represents the surrounding scope, and we can call getLength on that. So these are the three different ways that we can use method references. Okay, right. So now let's talk about Lambda expression performance, because there are some interesting things to understand about that. Okay, so the first thing is that, as we've already kind of discussed, there is functional equivalence in terms of the three different types of way that we can represent a function in Java. So we could have a Lambda expression like this. So I want to say for each, and then I'm just passing W as the word, for example, and then printing it out. Okay, so that's a Lambda expression being used. We could also do that using a method reference, which you've already seen. So we simply say system.out double colon print line. Great. Functionally equivalent to the one above. And we could also do it with an anonymous inner class, a bit more verbose, but exactly the same thing. So now we're saying we have to create a new instance of a consumer of type string, and we're going to override the accept method, and we're going to print out the word. Great. The important thing about these is that none of these do anything different. They all do exactly the same thing. But how they compile is different. So we look at anonymous inner classes. The key thing here, as the name suggests, is that we're dealing with a class. So when that code gets compiled, the compiler looks at what you've done and it says, you are trying to represent an interface, but you can't do that because you need a concrete class in order to generate an object of that type. So the compiler will generate a class for you, an anonymous class. And if you've got a class like foo, then you're going to see a class which is named something like foo$1 to represent the anonymous inner class that's being used by foo. The problem with this is you end up with what's called type pollution. So you're generating lots more types in your application than you really need. What you really want is a function. The other drawback to this is that because it is a class, at runtime, you have to load that class. So there's an overhead in terms of loading the class, there's an overhead in terms of initializing that class, and then from the point of view of using it, it has to be instantiated. That could place an additional load on your heap space, it could place an additional load on your garbage collector because you're generating objects, and that might result in more garbage collection than you actually want. So there are a number of things where anonymous inner classes are not necessarily the best way of doing it. If you look at Lambda expressions, because of this functional equivalence, you could simply implement a Lambda expression as the equivalent anonymous inner class. So the compiler could take that Lambda expression, convert it into an anonymous inner class piece of code, and then compile that in exactly the same way that you do in JDK 7 and earlier. And in fact, if you look at the way that Lambdas were developed, the first implementation did exactly that. So you use syntactic sugar, Lambda expression, convert it to an anonymous inner class, compile it, off you go. Problem with doing it that way is you are forcing an inner class on your code where you don't actually want it. What you really want is a function. And the decision was obviously made not to have a function type in the language, but it would be nice if we didn't have all the extra work involved trying to make a function type, but then ending up with lots of extra classes. So there has to be a better way of doing this, and there is. And the way that it's done in JDK 8 is through the use of the invokedynamic bytecode and method handles. The reason behind this is that if you look at the history of invokedynamic, this is the first bytecode that was introduced in Java since it started. And what its goal was to help languages that were being developed and compiled into bytecodes that weren't statically typed. So if you look at languages like, I don't know, JRuby, for example, not statically typed, so you can change the types of parameters and return types of methods at runtime. And in order to do that with a statically typed virtual machine instruction set, you have to do a lot of extra work because you have to test everything before you call the method, and you have to determine which method you're actually going to be calling. So invokedynamic was introduced in Java SE 7 to make life easier for compiler writers who were generating code for the JVM. In JDK 8, it was actually used by Java because in JDK 7, Java didn't use it. So in JDK 8, Lambda expressions use the invokedynamic bytecode. And the idea behind this is to say, okay, we want to do something in terms of using Lambda expression, but rather than fixing how we do that into the compiled bytecodes, we'll use the invokedynamic bytecode and we'll say, leave the decision about how this is implemented to runtime. So then the JVM can decide how it wants to do the implementation of that Lambda expression when it's actually running. And that way, if new methods are found of how to do that, better performing ones, it's very easy to change that because you can change it in the JVM at runtime rather than having to recompile your code and generate a new set of bytecodes. So, as I say, no fixed binary format, JVM can provide a different way of doing that. Now, if we look at how things work in terms of Lambda compilation, first thing is that the body of the Lambda expression has to be converted into a method. Now, I know I've already said, it's a function, it's not a method, it's not associated with a class. But in order for it to work in terms of being used by the JVM, it is converted into a method in terms of its compilation. Now, that's done in one of three ways. So the first is if you have a non-capturing Lambda. Non-capturing Lambda is one where you don't reference any of the variables from the surrounding scope. So, if you're doing something like print line, and, well, actually, that's probably not a good example. But if you're doing something that doesn't reference variables in the surrounding scope, it's non-capturing. To do that, it's very simple for the compiler, because all it has to do is generate a new static method in the class where the Lambda expression is being used, where it passes the arguments of the Lambda expression as arguments to the static method that it generates and the same return type. So all it has to do is insert the body of the Lambda expression into that new method. Very simple conversion. For a capturing Lambda, if it captures variables like static variables and things like that, then again it's fairly straightforward to use because the compiler will generate a static method the same way as we do for a non-capturing one, but this time rather than just passing the parameters that are the parameters of the Lambda expression, it will prepend to those parameters any variables that you reference from the surrounding scope that are static. So that way when the body of the expression runs, it has the variables as parameters that are being passed to the method, so it's able to work in that way. The third form is where you have an instance capturing Lambda. So the Lambda is actually referring to an object rather than static methods. So in this case, rather than creating a static method in the class in which the Lambda expression is used, it creates a truly synthetic method, which is one associated with that particular class, and then when objects are created, there's a method that's of that. So in this case, because it's an instance method in the class which uses the Lambda expression, it's able to refer to the surrounding object. So it's able to access the variables that way. So this is how we generate the method. One of three ways. We now have a method in the class which is using the Lambda expression. Where you use the Lambda expression, a call to invokedynamic is generated. And what this is called is the Lambda factory. So the idea is that you make a call to the invokedynamic, and that will return a reference to an instance of an object whose type is the functional interface that the Lambda expression represents. So that kind of makes sense. So we need some way of getting a reference to the object so that we can then call the method on it. And in fact, to do that, we also have a thing called the bootstrap method, which is the Lambda meta factory. And that uses the java.lang.invoke Lambda meta factory class. The important thing about this is in terms of the way that the Lambda expressions work, is that the call sites of the Lambda expressions where we use the meta factory are evaluated in a lazy way. That means that if you don't use that Lambda expression, you don't have any overhead associated with it. So this is quite an important thing from the point of view that unlike an anonymous inner class where classes get created and classes will be loaded and things like that, from the point of view of if you don't use a Lambda expression, then you don't have the overhead of actually calling the Lambda meta factory, so it's ignored, which means you get better performance by using Lambda expressions in that sense. The next thing is if we look at the differences in terms of implementation between Lambdas and anonymous inner classes. And you can break out what both of these things do into three distinct sections. In the case of Lambdas, the first thing is how you link to the reference to the class which is going to give you the method which is going to be called as the Lambda expression body. For an anonymous inner class, the equivalent of that is loading the class that you need to call the method in order to execute the anonymous inner class method. Now, from the point of view of comparing these two, Oracle did quite a lot of performance analysis, and there's a video online that you can find which talks about this in quite some length. So the team in Russia did a lot of work on this. And what they found was that if you look at the kind of comparison of these two, from a Lambda point of view, once you get through to what's called the hot path, so once everything is kind of settled down and you use these things a few times, linkage and class loading is about the same. So the effect of using Lambda expressions performance-wise is about the same as anonymous inner classes. So you don't get any advantage for using either. But from the cold path, which is where you start up, so if you're only using a Lambda expression a few times, obviously that's going through the cold path rather than the hot path, then Lambdas win. So Lambdas actually have much better performance in terms of the first startup bit because class loading is a lot heavier weight operation than the linkage that you need for the call site of the Lambda expression. So the net effect of that is that Lambdas win because in the first startup bit they're better, and then once you get to the sort of stable state they're about the same as anonymous inner classes. Second part is capture and instantiation. So capture for lambdas, how we deal with captured variables, instantiation for the anonymous in a class. And what they found there was if you look at the two, they perform about the same if you're using a single-threaded environment. So both will be about roughly equal. If you start using multiple threads and you've got multiple cores in terms of what you're doing with that particular part, then lambdas will win. So lambdas perform a lot better as the number of threads, number of cores increases. Anonymous inner classes don't get the same benefit in terms of the instantiation versus the capturing. The other thing that was found about the way that lambdas work in comparison to anonymous inner classes is that if you have a non-static anonymous inner class, then you actually need 50% more space to represent a reference to a captured variable than you do in a lambda expression. So again, it's a small thing, but it means that lambdas, again, come out ahead in terms of performance. And then the last bit is where both of the different ways of doing things invoke the method. Since they're doing the same thing, they're invoking a method, there's no difference between those two. So overall, what was found was that lambda expressions come out on top in terms of performance, which is what you would hope. Now, in terms of like rules of thumb, non-capturing lambdas automatically optimize. Just the way they work is that they're better in terms of optimization. Second thing is that method references are slightly more optimal. The reason for that is that, as I described to you earlier, one of the first thing that has to happen when a lambda is compiled is you have to generate a new method which has the body of the lambda expression in it. If you're using a method reference, you don't need to do that because you already have a method reference, so you don't need to create a new one to put a call to another method in it. So the compiler will simply ignore having to create a new method and will just use the method reference directly. So that way, if you use a method reference, it's actually more efficient than using the same code as a explicit lambda expression. The other thing that they found in terms of doing their analysis was that tiered compilation gave better results with lambda expressions. Now, the point is that tiered compilation is turned on by default, so the advice really is don't use minus tiered compilation. Don't turn tiered compilation off if you want better performance from your lambda expressions. Right, so that's performance. Okay, so now we've had the interesting and useful section. Now we're going to move on to the interesting but not so useful section. Right, so the idea here is how far can we take lambdas? Now I have to give credit to somebody else for giving me inspiration on this, because I think it was last year at a conference in Switzerland, there was somebody called Jarek Ratachki who did a presentation on lambda expressions. And I sat there and I watched it. He did it in an IDE, which was just blew me away. So he did it in an IDE, and he kind of did all this Java on the screen, and I looked at it, I thought, I have no idea what he's doing. And I had to think about it a lot, and I had to go away and sort of, I talked to him afterwards, and we kind of chatted about it, and so this is where we come from. Right, so the first thing is, we call all these things lambda expressions. Why do we call them lambda expressions? And the reason is because of Alonso Church. So Alonso Church came up with the idea of lambda calculus back in the middle of the 1930s. So clearly you kind of think to yourself, well, what does that have to do with Java, which didn't actually come out until 1995? So, 60 years later, Java comes out, and then it's another, like almost 20 years before we get lambda expressions. Now, the thing is that Alonso Church's lambda calculus was a mathematical way of representing any sort of way of processing things with functions. And so the interesting thing about Alonso Church was he was also the supervisor for Alan Turing when Alan Turing did his PhD in Cambridge. So there's the kind of interesting connection between lambda expressions, which is functional programming, and Alan Turing, who obviously did a lot of work on the design of the modern computer. So this is where we get into what I call exploding head lambdas. As Java programmers, we are very much accustomed to imperative programming. So we like to deal with loops, and we very much like to deal with state. So we have variables in our program, we have for loops, we have while loops, and so on. But the problem is that functional programming is not imperative. So I like to ask this question. And so everybody here is a Java programmer, I'm sure. So who would also consider themselves a functional programmer? Yes, you see, there's a few people, but not everybody. And that's really quite telling. All the audiences I talk to, this is very common. There are a few people who've done functional programming in other languages, but a lot of Java programmers are not functional programmers. And it does take a different way of thinking about things to actually do functional programming properly. Believe me, I've learned that the hard way. If you came to my Streams and Lambdas talk this morning with Stuart Marks, you'll see how badly I can write code using functional programming. Anyway, so the interesting thing about lambda expressions and lambda calculus is that lambda calculus and Turing machines are completely equivalent. Now, Turing machines, if you have a Turing-complete language, Java, C, C++, even JavaScript, is Turing-complete, then any problem that can be solved by a computer can be solved in that language. Lambda calculus is equivalent in terms of the way that they work to the Turing machine. So that means that any problem that you can solve with computation can be solved using lambda calculus. But it will give you a headache, believe me. At least it did me, and I'll explain a bit more of that as we go through. So the idea now is, what can we do in Java if we only use lambda expressions? So we're not going to use any primitive types. We're not going to use any operators. We're not going to use any, we're not going to use any objects either. So we're literally only going to use lambda expressions, and we'll have one functional interface. We have to have a functional interface in order to create a lambda expression. So what can we do with this? Right, so the first thing is our functional interface. So we'll call it, very originally, lambda, okay? And lambda is going to have one method, one abstract method called apply. Apply takes as a parameter a lambda expression and returns a lambda expression. So that way we can chain them together very easily. Good. So now we have to start off and think about how can we do things in Java if we're not going to use primitive types, we're not going to use operators. Well, the first thing is we need a lambda expression to represent identity. So identity is where you pass something and you get the same thing back. Great, so we can create a lambda expression called identity, and that returns a lambda expression where you pass it a parameter and it returns the same parameter. So it just gives you back what you give it. So far, so simple. And in red, I've actually used the lambda notation because sometimes it actually gets a lot easier to understand the lambda notation than it does the Java code. Right, so we have a lambda identity. For the first couple of slides, I'm also going to show you the equivalent anonymous in a class, because sometimes that makes it a little bit easier to understand. So in this case, we're creating a lambda called identity, which is a new lambda, which then has an implementation of the apply method, which takes a lambda x and returns x. Okay, all good. So next, we need some primitive types. So we're going to create Boolean representations, true and false. So we'll start with false. And in this case, false is a lambda expression which always returns the lambda expression which we have for identity. Okay, so we're getting a little bit more complicated. So we have a lambda expression f which returns another lambda expression which is the identity lambda expression. And again, if we just look at the equivalent anonymous in a class, we've just got 2 layers of lambda expression there. So nothing terribly exciting, but I'm not going to show you any more anonymous in a classes because it does get way, way too much code. The opposite of Boolean false is clearly Boolean true. So in this case, we'll have a lambda expression which returns a lambda which is never going to be identity. So in this case, we can say, okay, so it's the opposite of true. The opposite of false is true. Great. So we have a lambda expression which does that. So now we've got Booleans. Right. Next, we need numbers. So there are things called church numerals. Church numeral, we can sort of take some mathematical inspiration here, and we can say that the identity for addition is 0. If you add or subtract 0 from any number, you get the same number back. So it's the same as an identity. We already know what the lambda expression for identity is, so what we'll do in this case is we'll use the lambda expression for identity to represent the number 0. That makes sense. It's also kind of logical from the point of view of using our Boolean true and false. If you think about C programming, C language, if you've done C, in C there isn't a Boolean type. So if you evaluate an if statement, then the false value is 0. true is anything other than 0. So in this case, true is the same as the identity expression. So it's also the, so we end up with 0. So it kind of ties together. Great. The other thing is that you can think of it in this way, that the function f is being applied to the lambda expression 0 times. Now, you might look at that and go, okay, what does that mean if I apply this 0 times? But it becomes clearer if we look at 1. Okay, so the lambda expression for 1 is a lambda expression where we take x and then we apply x to the function f that we're passing. Like I say, this already starts to get a little, as a Java programmer, it was already starting to get a little bit complicated here. So that's what we do. We apply the function f to x and make that part of our lambda expression. And the key thing here is that if you look at lambda calculus doesn't use loops. So we would never use a for loop in lambda calculus. Lambda calculus does things repeatedly by, in effect, recursively calling the same function. So if we look at the lambda expression for 2, what we do is we apply the function recursively twice. So now we have x goes to f.apply of f.apply of x. Great, so, and you can continue with that as many times as you like to represent numbers greater than 2. I'm not going to do that because I think 2 is enough. You get the idea. Right. Now we need to look at how we can do some mathematics. So how about if we want to increase the number that we have by 1? Well, that's actually not too difficult, because if you think about it, what we need to do is we simply need to apply the function to that again. So the lambda notation shows that it's that way, and in terms of a successor lambda expression, we end up with n, which is our number, and then we want to apply the function f to that one more time, so we get f.apply of n.apply of f.apply of x. Okay, so the successor is fairly straightforward. We simply want to apply that function one more time. The predecessor, a little bit more tricky, because what we're doing is we're actually removing one call to the function. So that makes life a little bit harder. And I'm not going to explain this. I'm just going to show you what it is. So that's the lambda notation for it, because then we start getting all sorts of extra letters involved. So there's G, H, and U, and X. And the equivalent Java code becomes this. So it becomes quite sort of nasty in terms of, okay, it's N, F, X, N.apply, G, blah, blah, blah. We're not going to use that. So I figured that's rather complicated. If you really follow it through, it does actually work. I guarantee that. So then, let's look at how we can add two numbers together, almost into the kind of bit where we're going to do something interesting. So addition is simply repeated incrementing. So if I want to add n to m, it's the same as saying add 1 to m n times. So we already know how to add 1 to a function. So all we're going to do in this case is add 1 to the function n times. So we end up with this slightly more complex way of doing things. So we've got m, n, f, x, and all the applies. Great. Subtract, which again, we won't bother with going into too much detail. We'll use the predecessor function to shrink down some of the code, but we can do the same thing of repeatedly applying the decrement operation to decrement. Okay. So then I thought, right, we want to do something simple with lambdas. Let's add 2 plus 2, only using lambdas. Right, so we know the lambda for 2 is apply the function twice recursively. So that's straightforward, f, x, f.apply of f.apply of x. And we know that the lambda expression for plus is m, n, f, x, blah, 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 blah. Right, we need to combine these two. And interestingly, we can do that by simply saying, and this is Java code, lambda 4 equals plus, which is our lambda expression, and then we apply to that 2, and we apply to that 2. So we're calling it recursively twice with 2 values 2. And if you kind of write that out just as the mathematics, you end up with 4 equals plus 2, 2. And this is what's called Polish notation. I don't know about, for those of you old enough to remember, like very early HP calculators, I think, used reverse Polish. So this is forward Polish rather than reverse Polish notation. But you get the idea that in order to add things, we can actually do it only using lambda expressions. So we can say lambda 4 equals plus dot apply 2 dot apply 2. Right. How do we know that that works? Okay. So this is where it gets interesting, because what we'll do is we'll follow through the stages of how to actually show this. And I have to say that one of the things, when I was doing this, I was sitting at the table, and my son, who was 10 at the time, he came down and I was scribbling out stuff, and I was trying to work things out, and he said to me, "What are you doing, Daddy?" I said, "I'm trying to work out what's 2 plus 2. And he looked at me like I was stupid, and he said, "Well, that's easy, Daddy, it's 4. So I said to him, "Well, I'm trying to use lambda calculus for this." So I showed him the writing that I was in, and he just looked at me and goes, "No, it's 4. So anyway, so what we'll do is we'll take our addition lambda expression. So we have m and we have n that we're going to add together. So in the case of m, we're going to replace m with the lambda expression for 2. So we get a slightly longer lambda expression. I've highlighted in red where we replace m with the lambda expression for 2. So we also take m away from the front, because now we're in effect applying that to the function. And then what we need to do is the same thing for n. So n is 2 as well, so we'll replace the n that we have there with the lambda expression for 2, and we end up with quite a long lambda expression, but it doesn't quite look like 4 yet. So we have to do some reduction on this. So if we switch to that, what we now need to say is, okay, so we've got fx, and then we've got this bit here in blue where we're saying f is the lambda expression which is returning x goes to f dot apply of f dot apply of x dot apply of f. The nice thing about that is that f is we're applying f to that, but f is the variable, if you like. So it's quite a simple reduction. We just, in essence, take off the apply and remove f. So now we get x goes to f dot apply of f dot apply of x. And if we do the same thing here, we've got a lambda expression here where we've got f, and we want to apply f to that lambda expression, then we can do the same thing, which reduces down, so we get x goes to f dot apply of f dot apply of x. Then what we need to do is we need to take that which has been condensed down, but we've still got f goes to x, goes to x, goes to f of apply, and so on. But we need to apply this whole blue, and actually within the apply, we're going to apply x. And again, x is an easy one to eliminate because it's the same variable. So we end up with f dot apply of x. But now things are a little bit more complicated, because we have to apply, where we have x, the whole of this lambda expression, f dot apply of x. And that reduces down to, where are we? Yes. So we get that, we reduce that, x changes, yes. So then we reduce that, and we end up with f goes to x goes to f dot apply of f dot apply of f dot apply of f dot apply of x, which is 4. We have proved that 2 plus 2 is 4, and we've shown that we can do it only using lambda expressions. Like I say, it did take me quite a while to get that straight in my head. So just to summarize then, lambda expressions, very useful, very powerful, a nice succinct way to represent behavior. So you can pass it as a variable, you can assign it to a variable, you can pass it as a parameter. Better performance than anonymous inner classes. So if you're thinking, in terms of like performance programming, then lambda expressions are a better way of doing things than anonymous inner classes. Method references are even slightly better than lambda expression, explicit lambda expressions. And as I say here, you can use them in weird and wonderful ways, but I certainly wouldn't recommend trying to write all your code only using lambda expressions. If you want to do 2 plus 2 in Java, use the primitive int type, use the plus operator, much easier. More information, like I say, my inspiration came from Yarek's presentation. There's a video of him doing this at Vox in Zurich. And there's also what Yarek based his work on, which was Dixon Yang's blog, who works for Microsoft, and he did this in C#. So it's a similar kind of thing, but he's got a lot more detail about how this all kind of works out. So with that, thank you very much.